This is Euclid Book 10, proposition number 44. A second bimedial straight line is divided at one point only. Let AB be a second bimedial straight line divided at C. So now we have line AB and it's divided at C. So that AC, CB are medial straight lines commensurable in square only and containing a medial rectangle. This is by Euclid Book 10, proposition number 38. Okay, so now we have AC and CB, and those two lines there are medial straight lines. They're commensurable in square only, and they contain a medial rectangle. It is then manifest that C is not at the point of bisection because the segments are not commensurable in length. I say that AB is not so divided at another point. For if possible, let it be divided at D also, so that AC is not the same with DB. So AC, that length right there, is not the same as the length DB. As a matter of fact, we're going to say in just a second that AC is greater in size than DB. Because we can now say, but AC is supposed greater. It is clear that the squares on ADDB, okay. Once again, we're going to be drawing squares. First square has all four of its sides the length of AD. The second square has all four of its sides the length of DB. Are also, as we proved above in a lemma, which I produced just a little while ago, less the squares on AC and CB. Okay, so now we have to make two more squares. First square will be the length of AC. All four sides will be the length of AC. Second square will be CB. All four sides of it are going to be the length of CB. So the area of AD combined with DB is actually going to be greater than the area of AC combined with CB. And suppose that AD, DB are medial straight lines. So now we're going to suppose that AD and DB. Okay, there's AD and there's DB. Let's suppose that they are medial straight lines. They're commensurable in square only and they contain a medial rectangle. Now let a rational straight line EF be set out. Okay, so now we're going to draw EF. It's going to be a rational straight line. Let there be applied to EF the rectangular parallelogram EK. So this parallelogram EFKN is going to be made. That whole area is going to be a rectangle. And the area inside of this giant rectangle is going to be equal to the area in AB. So now we're going to make a square. I'm not kidding you. We're going to make a square with length of AB. So all four sides of that square are going to be AB. So the area in this square is going to be the same as the area in this rectangle. And let EG, okay, so now we're going to divide this up. We're going to have a rectangle called EG. This is a EHGF. EHGF is going to be a rectangle. Okay. So now we're going to apply to this Okay, sorry I lost my place there. Okay, so now let EG equal the squares on AC and CB. Okay, so now we have the area inside of EG. And that area inside of EG is equal to the combined areas of square AC and square CB. So if you add the areas of AC and CB together, you'll get the area of EG. Okay, and then we're going to subtract this whole EG area from EF and K. We're going to subtract this area from the giant area. Therefore, the remainder HK which is this area right here, is equal to twice the rectangle ACCB. So now we're going to draw a rectangle. Two sides of that rectangle are going to be the length of AC. Like this. Two sides of that rectangle are going to be the length of CB. Like this. Okay. So this area right here is going to be the same as twice the area of the rectangle we just drew. This is by Euclid Book 2, proposition number 4. Again, let there be subtracted from EL. Okay, so now we have a rectangle EFLM. Okay. And the area of EL is the same area that if you were to take the squares of AD and DB and you added those together, okay, you have the square of AD, you add that area to the square of DB, you add those two areas together, and that's this area right here, which were proved to be less than the squares on ACCB, and that's by the lemma, which we covered a little while ago. Therefore, the remainder, MK. Okay, where's MK? Well, you have MLKN. Is also equal to twice the rectangle ADDB. So, we're going to draw another rectangle. Two sides are going to be the length of AD. Two sides are going to be the length of DB. Okay? And if you take that rectangle and you take its area and you multiply it by 2, then what you'll get is the area inside of MLKN. That area right there. Okay. Now, since the squares on AC and CB are medial, then EG is also medial. Okay, so we're saying now that the area inside of EFGH is medial. And is applied to the rational straight line EF. Therefore, EH is rational and incommensurable in length with EF. So, EH, which is this line right here, okay, and EF, which is this line right here, EH is rational, okay? This line here is rational, but it's incommensurable in length with EF. So this length and this length are not commensurable, and this is by Euclid Book 10, proposition number 22. For the same reason, HN is also rational, so this line here, HN, it's rational, and it's incommensurable with length of EF. So HN and EF are not commensurable. And since ACCB are medial straight lines commensurable in square only, therefore AC is incommensurable in length with CB. So this length right here is incommensurable length with this length right here. Now we're going to make a ratio of lines. First line AC. Second line CB. So as AC is to CB. Okay. So the square on AC, okay, remember we're not, the second part of this ratio is a square. It starts with a square, and that's the numerator, okay? So it's AC, all four sides, okay? So what's the denominator? What is the denominator if if the square on AC is the numerator? Well, the denominator is ACCB. Okay, so there's a rectangle, and two sides are going to be AC, two sides are going to be CB. So that's going to be the denominator of the second part of that ratio. But the squares on ACCB are commensurable with the square on AC. For AC and CB are commensurable in square. Now we're saying that if you were to make a square out of this line, and you were to make a square out of this line, those two areas would be commensurable. And this is by Euclid Book 10. Let's see. Proposition number 11. Okay. No, I'm sorry. It's going to be by Euclid Book 10, proposition number 15. Again, I got lost. And twice the rectangle ACCB is commensurable with the rectangle ACCB. So, if you have rectangle ACCB and you multiply its area by 2, that area is commensurable with the rectangle ACCB, and this is by Euclid Book 10, proposition number 6. Therefore, the squares on ACCB are also incommensurable with twice the rectangle ACCB. And this is by Euclid Book 10, proposition number 13. But EG is equal to the squares on AC and CB. Okay. So the area of EFGH, that area, is equal to the sum of the squares of AC and CB. So you take the area out of AC, you add it to the area in CB, and that whole area is EG. And HK is equal to twice the rectangle ACCB. So what's HK? It's HGKN. This area right here is equal to twice the rectangle of ACCB. So you take rectangle ACCB and you multiply its area by 2 and you get this. Okay. Therefore, EG is incommensurable with HK. So the area inside of this is incommensurable with this area right here. So that EH is also incommensurable in length with HN. Okay, so line EH, right here, is incommensurable in length with HN. This one right here. And this is by Euclid Book 6, proposition number 1, and Euclid Book 10, proposition number 11. Now, EH and HN are rational lines. Therefore, EH and HN are rational straight lines commensurable in square only. But if two rational lines commensurable in square only be added together, the whole is irrational, which is called a binomial. This is Euclid Book 10, proposition number 36. Therefore, EN is a binomial straight line divided by H. Okay, so EN is a binomial straight line divided by H. In the same way, EM and MN. Okay, so we have EM here and MN right there. Will also be proved to be rational straight lines commensurable in square only. And EN will be a binomial straight line divided at different points H and M. Okay. So this line here will be rational. I'm sorry, it'll be binomial. This line here is binomial. And it will be divided at different points of H and M, which it was. Right there and right there. And EH is not the same with MN. Okay, so we can't say that the length of EH is the same as the length of NM. For the squares on ACCB are greater than the squares on ADDB. So if you were to add the areas of the two squares AC and CB, and then you added the areas of AD and DB, you would find that the areas of ACCB are greater than the ones on ADDB. But the squares on ADDB are greater than twice the rectangle ADDB. So that means that you're going to take the two areas, AD, you're going to add it to DB, and then you're going to find out that those two areas combined are greater than twice the rectangle of ADDB. So we have rectangle ADDB. You're going to multiply that area by 2, and you're going to find out that it's actually less than the two squares that we just added together. Therefore, also the squares on ACCB, that is EG. Okay, so now we're going to be talking about this whole area right here, EFGH, this area right here, is much greater than twice the rectangle ADDB, which is MK. So, EFGH is greater in area, apparently much greater than area, than MK. So you have MLKN. So this area is greater than this area. so that line EH is greater than MN. So EH is longer than MN. I know it doesn't look like that diagram, but it will be. Therefore, EH is not the same as MN. Wow, what a proof. Alright, I will tell you more in a future video. Stay tuned.